Welcome students to the chapter 10, Light, Reflection and Refraction. Light is a form of energy which helps us to see objects. When light falls on an object, it reflects a light, and when the reflected light reaches our eyes, we can see the objects. Light always travels in a straight line, and this is called as rectilinear motion of light. In this chapter, we will be learning about common phenomena of light, like formation of shadows, formation of images by mirrors and lenses, bending of light by a medium, twinkling of stars, that is also because of refraction of light, formation of rainbow, also by refraction of light. Also, we will be learning about scattering of light, because of which we can see blue skies, yellow skies, red sky, white sky. So, light is an electromagnetic wave. It does not need any medium to travel in space. It travels in a straight line, and the speed of light in vacuum is 3 into 10 raised to 8 meter per second. It is a transverse wave. Here you can see the rectilinear propagation of light, that is, the light travels in a straight line. It is an experiment which this student has done with keeping 3 cardboards and a hole all together coordinated with each other. And there is a burning candle. The flames can be seen clearly in a straight line through the 3 holes by the student. If I move the cardboard, one of the cardboard, say the middle cardboard, little bit on the side, and we will see that the hole is not in a straight line, then what will happen? The light will not be seen by the person. Let us understand the meaning of reflection of light. Whenever light falls on a shining medium or any of the opaque medium, what will happen? It will reflect back in the same medium. It does not pass and go to another medium. Then we called it, when the phenomenon is called as reflection of light. Let us take an example of a mirror. Do you know how a mirror is made? It is a plain glass, and in a plain glass, on one of the surface, a shining silver color is done, and behind the silver color, a dark color is done. It has been made opaque and shiny, and when light falls on that surface, what will happen? It will be reflected back. Light will not go on the other side. It is opaque in nature, and light is not going to pass in that. We can see different objects like the table. I can see the whole part of your nose, eyes. So light is reflecting even on us. And from different angles, it reflects back. Our faces and our body is not even, it is uneven. So what happens when light falls on an uneven object? It will reflect back accordingly in different sides. You can see this light falling on a surface, it is reflecting back here. This light falling at another angle, it will reflect back on this side. This ray of light, that is incident ray, will reflect back. So the light reflects back, and this type of reflection on an uneven surface is called as diffused reflection. So reflection of light, the light that falls on an object is called as incident ray, and the light that goes back in the same medium is called as reflected, reflected ray. And at a 90-degree to the mirror is a normal. And the angle between the normal and the incident ray is called as angle of incidence, and the angle between the normal and the reflected ray is called as angle of reflection. There are laws of reflection that you will have to learn. First, the incident ray, the reflected ray, and the normal to the reflection at the point of incidence lies in the same plane. Which is a point of incidence? This is a point of incidence. We have taken this as a reference point. So at this point, let an incident ray fall on it. And from this point, the reflected ray will go. So from here, we have to take a normal. Normal means it should be 90 degree to the surface. So this is a surface, straight, this over here. And therefore 90 degrees this, and therefore this is called as normal. The second law is the angle which the incident ray makes with the normal is equal to the angle that the reflected ray makes with the normal. Again, I will show the angle, this angle I is always equal to angle R. It is written here, angle I is equal to angle R. So angle of incidence is equal to angle of reflection. This is 60 degree. This has to be 60 degree. This is again an example of angle laws of reflection. We will be studying about mirrors. Mirrors are reflecting surfaces. The rays reflect back. There are three types of mirrors that we are going to study. One is a flat mirror, one is a convex mirror, and one is a concave mirror. Flat mirror, everyone has seen it as it is at their place, at their house. Which type of an image you can see? You can see the image of the same size in front of you. The image that is formed is called as virtual image and is of equal size. In a convex mirror, that is a curve outside. If I take a ball, it is a spherical ball. And if I cut it in from between, and if I color the silvery part on the outside, the silver color, so that the light reflects back from it, then that curved outside part is called as a convex mirror. And such convex mirror will always give a virtual image, and this image is always smaller. In a concave mirror, if instead of the outer part, if the inner part, the cave part, the inner part is made shining, then what will happen when light falls on such a surface? It will give images that can be virtual also, it can be a real image also, and the sizes can be different. It depends upon the position of the object in front of the mirror. So just remember, flat mirror, which type of an image is formed? Virtual and of equal size. Convex mirror, which type of image is formed? It is smaller and virtual. And in concave mirror, which type of an image is formed? We can get virtual images also, and we can get real images also. And the sizes can be different from a point size to a very large size. I will be explaining you about virtual images and real images. What do you mean by virtual image? The virtual image means when the reflected light meets, actually they both meet. When the light is incident on an object, the light reflects back. When these reflected rays actually meet, then the image formed is called as real image. But if they do not meet, and we just extend it with an imagination on an opposite side, and that means we say they appear to meet, then such an image is called as virtual image. You just have to say that when the reflected rays do not meet, the image is formed as virtual. Virtual images are always erect. So you can see the mirror that is a flat mirror in your house, everyone is having. If you stand in front of that mirror, the image formed is virtual image. It is straight. So even in convex mirror, if the virtual image, it is smaller, but it is always straight. It is not upside down, like our head down and legs up. But in a concave mirror, if the virtual image is there, virtual means the image is always erect, that is straight, erect we call it. And in real image, the images are always inverted. This is a reflection done by a plane image. See, a person is standing in front of a plane image. Remember, whenever we are drawing a mirror, a plane mirror or a curved mirror, the lines on the back indicates that that side is opaque, and the line in front of it, that a black line over here, this surface on the front of that surface, it shows which type of which is the surface? Shining surface. Okay. So this image from the person falls on the mirror. So imagine from different places it is falling. We have taken two incident rays that are falling. What will happen? It will reflect back at the same angle. So this ray is reflecting back here and this ray is reflecting back here. You can see these two rays are not going to meet. Imagine the distance over here. See, it is less. And now you can see the distance over here. It is increasing. That means as we move ahead, the distance between two rays are going to increase. So they're not going to meet. Therefore, which type of an image is going to take place? A virtual image. And virtual images are always erect. Now, I said they appear to meet. So I've extended it on the back side of the mirror. And they are meeting. So in a plane mirror, the image is always formed behind the mirror, we call it. It is a virtual image because they are not meeting, and it is the incident ray, the reflected rays are not meeting. You'll have to say it is a virtual image because the reflected rays are not meeting, but they appear to meet, means I'm extending back and they appear to meet and they're forming an image. The plane image, the size of the image is going to remain the same. So now you might understand what is the meaning of real image and what is a virtual image. Image of real images always can be obtained on the screen. The virtual image cannot be obtained on the screen. The real image, the reflected light actually meet. That is a light after reflection meet. But here the lights do not meet, but they appear to meet if I extend it on the backward side. The real image examples are image formed on the cinema screen, then image on the retina of the eye. On the retina of our eye, the image formed is always inverted. The image formed by the plane mirror is a virtual image. That is an example. So what is the image formed by the plane mirror? It is always erect. It is of the same size. It appears to be at the same distance from the mirror as the object. If you move backward, the image will also move backward. That is, the distance is going to remain the same. It is virtual and it is laterally inverted. Laterally inverted means you can see if you write a letter ambulance and just keep it in front of the mirror, you will see the position of B and few of the letters, how they are inverted. Even when you are standing in front of the mirror, you'll wherever the direction of your left arm is there, on that side, the right arm is there. So real and virtual image. This is a plane mirror. This is an object. One of the ray is going straight. Whenever any ray is normal to the surface, 90 degree, it will come back. So that is a rule. A ray is going straight, it is going to come back. And another ray is meeting at the pole. What is happening? It will reflect back at the same angle. Now, this is a reflected ray and this is a reflected ray. What will happen if I extend this on this side and if I extend in this? What is happening? The distance between these two rays are increasing slowly and slowly. That means they are not going to meet. But if I extend it on the backward side, they are meeting. So on a plane mirror, the image is formed. Behind the mirror, the distance of this object distance, that is from here to here, and from the image distance from the pole towards the image side is going to remain the same. The height, object height is always referred as h. The image height is always referred as h dash. H is equal to h dash over. Now, the real image, what will happen in the real image? Real image means actually the rays are going to meet it. Here the rays are not meeting. So for this image is a virtual image. What is a spherical mirror? Spherical mirrors are those type of mirrors which are a part of a hollow sphere. Let us take a ball. It is spherical in shape and it is hollow. Hollow means inside it is not filled up. So the sphere is hollow. If I cut the ball into half, I can make two types of mirrors from that. If I make the inner part shining, I can get a concave mirror. And if I make the outer part shining, then I will get a convex mirror. When I make an inner part shining, I have to keep the outer part opaque. Only one part shining, I will be doing it. Cave means the inner part. You know the cave, it has to be an inner part. So that is a concave mirror, inner part shining. So how will you show that concave mirror figure? Just see, this is a blue color, means I've made the inner surface shining, and then I have to draw lines over here, showing that it is opaque on that side. So this is a which type of mirror? Concave. And outer surface is shining. Inner I have to draw lines. This indicates what? That this is a convex mirror. So spherical mirrors are concave mirror and they are convex mirror. Now I have to give the different parts of the spherical mirror. Since I told you I took it from a ball, it is spherical in nature, it is hollow in between, so it has got a center. So if I make this whole circle and if I put a dot in between, what will happen? It is called as a center of the curved surface. And this center of the curved surface is called as center of curvature. And this distance and the point, this point is called as a pole. The center of the reflecting surface of a spherical mirror is called as a pole. If I make a line joining the center of curvature in the pole, it is called as a principal axis. So what is a principal axis? It is a line joining the center of curvature and the pole. Now I have to draw focus also over here. So there are many definitions for the focus, but between C and P, exactly at halfway, I can put F over here. I can always say that 2F is equal to C. So this distance between the C and the P, it is the radius of the whole of the circle. Can I say this is center and this is P? So this is a radius. So what is the radius of curvature? Radius of curvature is the distance between the center of curvature and the pole. Center of curvature is a point and radius of curvature is the distance between the, and where will the focus come? Exactly between the pole and the center of curvature. Similarly, I can draw that of a convex mirror. You can see this side, I can make the whole sphere. I can put a center of this. Then the distance between the pole and the center of curvature, it is called as a radius of curvature, and in between I can put the focus exactly in between. So which side is shining, a concave mirror is from inner side, and if the outer surface is shining, which type of a mirror is formed? Convex. So if this is a sphere they have taken, if I cut on this side and make shining the inner side, concave mirror is formed. So imagine this whole sphere and this is a center. You know what is a center of curvature? It is a point. This will be the radius of curvature. One side only you can put. So mirror has a radius of curvature, that is R. It is a distance. Center of curvature, it is just a point. Here they've given point V, we normally call it as a point P. Also you can write this pole. And principal axis is a line joining the center of curvature and the pole. The definitions are here. What is a pole? It is a center of the reflecting surface, and usually it is represented by the letter P. The center of curvature is the center of the sphere of which the mirror is formed. It is represented by C. The radius of curvature is the distance between the center of curvature and the pole. The principal axis is a line joining the pole and center of curvature. The focus is a point on the principal axis, during which all the rays parallel to the principal axis actually meet in a concave mirror or appear to meet in a convex mirror. Yes, I will be teaching you the difference between the actually meeting and appear to meet. Actually meeting means a real image. Appear to meet means we are extending the line and we are making the rays join together. That is why we have to say appear to meet. And appear to meet always takes place in a convex mirror because the image is always going to be virtual over there. And the focal length, it is the distance between the pole and the focus. And it is represented by symbol F. So this is a spherical mirror. If I make the whole mirror this sphere, I have to make still bigger. Oh my God, this has become the smaller one. So I'll have to draw the sphere like whole big like this. And inside this is a C. So this is C, this is the center of the curved surface. On the curved surface it becomes a pole and the whole distance is radius of curvature. And where will you keep focus? Exactly between. So don't draw a curve, put F and put C. No, don't do like that. Just take a hint that whenever you're drawing a spherical mirror, draw a half circle and imagine that the full circle will be like this and put a dot in between like C in the center. And between the two exactly put F. If you do that, all the figures of the ray diagram will come exactly correct. Okay, so this is again a concave mirror and convex mirror. Always draw these lines showing that it is opaque in nature. Okay, here they have shown the line as a shining object and the blue thing shows that it is opaque. Blue means it is opaque and this side is a shining. So this is this is a concave mirror and this is a convex mirror. So concave mirrors are which type of a mirror? They are converging mirror. So when the parallel rays are falling on this object, this here is a shining surface. So the cave is a shining surface. So when the ray of light is falling on this, they reflect back and they meet at a point, and that point is called as a focus. When this line, this ray that is falling, coming from here, the principal axis, it is normal, 90 degree, exactly at the center. It will always come back in the same direction. See, the principal axis, the rays of light is falling on the pole center. It is coming back. Two rays are shown over here. One is going towards here and one is going. Others rays, so you can see when they're falling at an angle, this is going straight. It is coming on this side. This is going straight. It is passing through the focus. So parallel to the principal axis, the ray of light will always form at the focus. So this is how you can find the focus, and this distance will be always between the center of curvature and between means half of the way. Now this is written wrong. Here you take it as convex mirror. Make it convex, V-E-X. Okay, this is convex. So the outer surface is shining. The blue color inside is not shining. So when the rays are coming on this shining surface, what will it do? They are diverging. They are not meeting. Here they are converging. And here it is diverging. So what? Only the middle ray, if it goes, it will come back in the same direction, principal axis. So here they are diverging. So convex mirror is called as a diverging mirror. And when I extend it on the backward, what will happen? They meet at a point that is called as a focus. Okay. So just change the word over here. Don't remember this word concave. It is convex, please. The spherical mirrors are two mirrors. Now I think you have very good and very efficient, and you can say very well about the concave mirror and convex mirror. A concave mirror, both the concave mirror and the convex mirror are curved mirrors. The concave mirror is which type of a mirror? It is a converging mirror. Which type of a mirror is a convex mirror? It is a diverging mirrors. And the converging point is a focus when the parallel rays to the principal axis fall on the concave mirror. They reflect back at a point that is called as a focus, and they reflect back, but when they are extended, they appear to meet at focus. So here, which type of image will be formed? They're meeting a real image. Which type of an image will be formed over here? Virtual. Dotted line, you have to make it when they appear to meet. So we will be learning about the rules to make a ray diagrams. The first rule is that when the ray is parallel to the principal axis, this is a principal axis, this, and when the ray is parallel to the principal axis, it will reflect back and it will always pass through the focus. That is a concave mirror. Converging. It will always converge and pass through the focus, and this is the case of concave mirror. In case of convex mirror, it is a diverging mirror. So when the ray is parallel to the principal axis, it will diverge. But when you are extending, it is going to meet to the focus. So the statement remains that when the ray is parallel to the principal axis, the reflected ray will always pass through the focus. Okay. The second rule, when the ray is passing through the focus, the reflected ray will be parallel to the principal axis. See over here, it is passing through the focus. Here, if I extend passing through the focus, it will remain parallel to the principal axis. Just draw it. Practice this while saying this again. Rule number 3, if the incident ray is passing to the center of curvature and is falling on the curved surface, you have to make the curved surface so long that it should fall to here. It will come back in the same direction. You're going to make one ray, but 2 arrows opposite side. One is coming on this side and again reflecting back. Here also you can draw. One is coming here, dotted line appear to go, but from here it is reflecting back. Rule number 4, when a ray of light is incident on the pole at a particular angle, what will happen? It will reflect back at the same angle. That is how you have to draw. The angle of incidence is always equal to angle of reflection, F-L-E-C-T-I-O-N. So here, but the incident principal axis always goes straight and it will come back straight. Okay, so don't worry about the principal axis, which direction you have to show. Here is an extra sheet. You just have to draw. This figure looks odd when you are drawing, so please don't draw like this. Here I have shown this, this figure only to let you know that how can a question be asked. First, the question is, which type of mirror is this? So you can see it is shining inside. The dot lines on the back shows that it is opaque on that side. So which type of a mirror it is? It is a concave mirror. What is the position of the object? This is center of curvature, this is focus. So it is beyond C. What is the position of object over here? It is between C and F. And what is the position of the object over here? Within the focus, between the F and the pole. But when you are drawing, make a circle in such a way that like this should be the C, and between C and V, it should be the V. Okay, with this, you won't get a figure right. Clear? So these are the questions that I will be asking, and you can draw the figures accordingly. You have to apply rules over here. Rule number 1, 2, and 3. Mainly all the 3 rules you will have to use. So these are the ray diagrams which are made made on the concave mirror. We have learned that in front of, by the reflection in front of the concave mirror, the images formed can be real also, it can be virtual also, and it can be smaller also, it can be larger also. One thing you take care that a virtual image over here is always large. Convex mirror, the virtual image is always small, but concave mirror, the virtual image is always going to be large. So let me tell you, where is the virtual image formed? Oh, here the reflected rays are meeting. Here also the reflected rays are meeting, real image. Here also the reflected rays are meeting. One is this and one is this. Here also the reflected rays are meeting. One is this and one. Here also they appear to meet at infinity. Okay, they are back, I cannot extend. But here what is happening? I've made a dotted line. This indicates that the virtual image is formed. So only one virtual image is formed over here. One. So what is the object size here? What is the image size? Larger. So in case of a concave mirror, a question is always asked, when is a virtual image formed? A virtual image is formed when the object is placed within the focus. See, between the pole and the focus. And where is the image formed? Behind, it is large and virtual. So which is the type of the image? Virtual. What is the size of the image? Large. So just remember this very well. Many a times only this is asked in the exam. So you should know the object where it is placed. Let the object be AB. It is within the focus. So one of the ray will go straight. What happens? It will passing through the center of curvature. So what is going to happen? They have used the arrow double side. One is going and one is coming back. Okay, you have to use rule number 3. Rule number 3 is which one? I'll show you. This ray of light is going, it is coming back. In case of concave mirror, I'm showing concave mirror, so I'm showing you this. Okay, so the ray of light is passing to the center of curvature from which you touch the object, because we are interested in seeing the reflections that is being done from the object. So this is the ray straight, extended on the back side. Another is rule number 4. It is going at the pole, it will come back in the same direction. Imagine the distance between these two is increasing. See, they're never going to meet. So we have to extend it on the backward and they will appear to meet. And then virtual images are always erect. And in case of concave mirror, the virtual image is larger in size. Okay, I think you will know it very well. Which rules have I applied over here? Rule number 3 and the rule number 4. Now let us start by keeping the object in different places. All these are real images. So the object is at infinity. See the sun. From the sun, all the rays are coming parallel. And when the rays are parallel to the principal axis, what will happen? They will pass through the focus. So which type of object image is formed? First of all, the rays are meeting. See here and here, they both are meeting. It is a point. So the image is point-like, real, and real images are always inverted. Clear? Here, where is the object placed? Beyond C. Which type of an image it is formed? The rays are meeting, you can say real. But you will have to apply the rules 1, 2, 3, and 4. Which rule I am applying? Rule number 1. It is the incident ray is parallel to the principal axis. This is a principal axis. Okay, I'll have to say this is a principal axis. So incident ray is parallel to the principal axis. What is happening? It will reflect back and pass through the focus. So you have to draw the arrows also. Here, one arrow straight, it is reflecting back. Second, rule number 3. Reflecting the incident ray is passing through the center of curvature. It should come till here. It is reflecting back. Now these and these two are meeting at this point, so it is a real image. It is an inverted. Wherever you see the arrows that are touching, say this side, the two rays are meeting, so this is the upper side, and this two place the two rays are meeting, so this the arrow point should be over here. So an inverse image is formed. Inverted, we say. What is the size of the image? We put it A dash B dash. The A dash B dash is smaller in size than the object AB. Okay, what is the position? It is between C and F. So you'll have to write position of the object beyond C, position of the images between C and F, type of images, real and inverted, and what is the size of the image? Smaller than the object. Now let us go to over here. Likewise, the object is placed at C. So which rules are we applying? Rule number 1, the ray is going straight, parallel to the principal axis. Which is a principal axis? This pole between C and P, this is a principal axis. So this ray is AD is parallel to the principal axis. It is reflecting back with at F. So rule number 1, principal ray is parallel to the principal axis, it will always pass through the focus. And rule number 2, when a ray of light is passing through the focus, it is parallel to the principal axis. The reflected ray submitting at point A dash and an inverted image is formed. The image size is same. The AB and A dash B dash size is same. So again, we can write position of the object at C, position of the image at C, and type of the image, real images are always inverted, and the size of the image is of the same size. Now we are bringing the image closer. See, at infinity, this was beyond C, then at C. Now what is the position tool? Between C and F, C and F. I'm bringing it closer between C and F. This is an object. This is a principal axis. So when I'm putting a principal, always try to label it, okay? And put your own labels. If you're not understanding this labels, you can put. But you'll always try to keep the object as AB and image as A dash B dash, okay? Now over here, this is an object. It is placed between the focus and center of curvature. Which rule are we going to apply? The rule number 1. The incident ray is parallel to the principal axis. It will reflect back and pass through the focus. Second, which rule? Rule number 3. From the height of the object, allow it to touch to the center of curvature and then extend it to here. So the ray is passing through the center of curvature, it will come back. See, from here the ray is going straight over here, it will come back. Extend it. Where the two rays are meeting is this. When that we have kept an arrow, you can name it A dash B dash. What is the size of A dash B dash image? It is larger than the object AB. So here what can I say? Position of the object is between C and F. This is the position of object. Then what is the size of the position of the image? It is beyond C. Okay, beyond C. What is the type of image? It is real because the rays are meeting. Real image is always inverted. And what is the size of the image? It is larger than the object. Now we will bring the object further closer. That is which place it will be F. So here it is F. This is an object at F. AB is at F. Rule number 1 apply. The incident ray is parallel to the principal axis. It will always pass through the focus. Always pass through the focus. And what will happen? Rule number which one? Rule number 3. From the height of the object, allow it to pass through the C and extend a line up till here. So when a light is passing, incident light is passing to the center of curvature, it will come back in the same direction. Let me extend it. It may meet at infinity. Okay. So where is the image from? At infinity, they will meet. Therefore, it is a real and inverted image. And what is the type of image? Highly enlarged. It is opposite to here. At infinity, point-like. And the image is formed at focus. And at focus, at infinity. Now, we have already done this. When it is kept within the focus, the image obtained is virtual and direct. Which rules are applied over here? The rule number 3 and rule number 4. Rule number 3 means at the center of curvature, the incident ray passes, it will be reflect back in the same direction. And rule number 4, the angle of incidence is always equal to angle of reflection. Please try and draw all the ray diagrams. They are very important. So these are the ray diagrams of a convex mirror. We had studied about the concave mirror. Convex mirror, one rule is there. I had told you before also, and again I'm repeating. I started it from the slide number 1 also, that this, in case of convex mirror, there is an error in the spelling CONVEX, right? N also. So in case of this, you can always say that the image formed is always virtual and it is always formed. Just take the example of a mirror that is placed on the vehicles to get the rear view. It is on the 2-wheelers or on a 4-wheeler or on a 3-wheelers. There are always mirrors near the drivers on both the sides of the driver to have a view of the rear side. And the image formed is always small, erect. You cannot get an inverted image. When the image is erect, it is virtual, and it is a small. It is not a larger one. And it is written on that mirror that the object is nearer than you feel it. You can just read what is written on that mirror. So wherever you keep it in front of the mirror, the object is always going to be small. That you can see while driving a car, wherever the car is, the car images, even when it passes near you, it will always be small. It will never be large. So here, if a question is asked that in front of a convex mirror, an object is placed as C, what will be the type of object, image form? Convex mirror, never see the position. Always write virtual and small. If it is kept at F, virtual and small. If it is kept at within the focus, virtual and small. Okay, so here at infinity, the example is virtual and small. Upright. Virtual means always upright. Virtual means upright. Virtual means upright. And here all the answers will be virtual, upright, diminished. Virtual, upright, diminished. Virtual, upright, diminished. So I'm not going to say. The image appears larger in size when the object is nearer to the object. So just remember, larger in size means, but it will be always smaller than the object. Okay, so here at infinity, the object is at infinity. Where is the image formed? The image formed will be always a point like we have already studied. Object is placed. Yes, I just went wrong over there. The object is placed at infinity. So the rays are coming from object from a distance, and the image is formed on the other side. It is virtual and erect. Please understand this. Okay. Now the second one is, this is a at a distance from the mirror. It is just a fit. This is a mirror. This is a convex mirror. This is a shining side on this. The object is placed over here. Rules you want to understand? Yes. Parallel to the principal axis. It is a diverging mirror, so it will go back, but if you extend it, it will pass through the focus. So which rule number? Rule number 1. Second rule is rule number 3. Extend it to the center of curvature, it will come back in the same direction. They are going to be, the image formed is smaller, virtual and erect. We are going to bring this object further closer. What is happening? Rule number, which one? 1, parallel to the principal axis, will pass through the focus. Extend it with the rule of convex mirror. Okay, and another one is, the object is passing through the center of curvature. Here, this is a center of curvature. The tip you have to take it. Okay, and that. So this size was this, and this was larger. So the image is going to become a little bit larger, but not larger than the object. It will be always smaller than the object. That is what it is written. As I'm bringing closer, it will become a little bit larger, but never equal or never larger, always smaller. Okay, the answer is going to remain 1 only, virtual, erect, and smaller. Next, this is a chart. You have to understand this chart very well. I've explained it very well. I'll just explain you how to learn. The positions of object is there. First it was kept at infinity, then beyond C, then at C, between C and F, at F, and within F, that is between F and P. Where is the position of the image form? At infinity, it was at focus. Beyond C, it was between C and F. At C, the image is formed at C. Between F and C, it is beyond C. At focus, at infinity, and between the pole of the mirror and focus, appears to meet behind the mirror. All the above cases over here, the image is real and inverted, except within the focus, the image is virtual, erect, and magnified. Just remember, this is a concave mirror. And in concave mirror, if a virtual image is formed, it is always magnified. Erect is there, virtual and erect is there, but it is magnified. And if in case of convex mirror, the virtual and diminished. So remember that convex mirror, virtual and diminished, and concave mirror, virtual and magnified. Rest all the images are real and inverted. And as you're going to bring the object closer and closer, the object size is going to increase in size. Like it was point-like, it increased in size little bit more, then it became more, that is equal to the object, it magnified, and it was highly magnified again. Okay, and that is how you're going to learn. And remember the uses of concave mirror. In one mirror you have learned is about a shaving mirror, or makeup mirrors, or a dentist mirror, floodlights, then car headlights. These all are the things, mirrors that are used in our daily life. Please learn the uses very well. So ray of a convex mirror, I've already explained. You can see over here again and again regarding this. Okay. Convex mirror, again and again, virtual, upright, smaller. Please remember, again and again, I'm repeating, virtual. And this is again a question that is asked, because only sometimes they will confuse you by asking you the question that if it is at F, if it is C, if it is infinity, any position it is, let them name the position. The answer is will be only one, virtual, upright, smaller in case of convex mirror. Okay, again, this is just to make you realize how many rules are applied over here. You just have to remember. One rule is which one? Parallel to the principal axis will pass to the focus. Rule number 4. Okay, apply these rules. Rule number 1 and rule number 4. You can see such curved mirrors with the help of your spoon at your home also. There are two sides. Okay, and in between there is an opaque. So the once if you're seeing on one side, you cannot see the other side. Okay, that means it is opaque. So when you're seeing with the cave part inside, cave, this is a cave part, you'll always keep your position and just move ahead, up and place. You will see the different positions. It is inverted, indicating that the rays are meeting. So just move it and the size may change. But in case of convex mirror, on the back side of the spoon, just move it, the image is always going to be smaller and always erect. Just you can check up at your place. So concave mirror, where are they used? They are used in flashlights because they give parallel beams. You can know where the position will be. Telescopes, they are used to collect light from distant sources and focus it for viewing. Cosmetic mirrors, so you can see the larger part of your face and facial part, and you can do the makeup accordingly, and the headlights of the car. Uses of convex mirror, they always image produces virtual, upright. They are used for the security mirrors and also the rear view mirrors. Okay. Again, these are the uses of concave mirrors and the convex mirrors. If you want to write from one page, you can just note down. Now, we are interested in knowing the sign convention for the reflection of spherical mirrors. There are negative signs and there are positive signs. Just if you see the concave mirror, U means the object distance, V means the image distance. Object distance, F means the focal length, R means the radius of curvature, H means the height of the object. The H can be real also, it can be virtual also. So let us understand, in case of a concave mirror or a convex mirror, U is both going to be negative. Why negative? I will show you in the next slide. Okay. Remember that U is always negative in case of concave mirror or a convex mirror. But V, that is, U means object distance, but V, that is the image distance, can be different. If it is a real image, it is negative. If it is a virtual, it is positive. So behind the mirror, it is positive. See, in case of mirror, behind the mirror, it is positive. No image is formed in case of convex mirror, so no need to write. Virtual means always positive, real means negative. So imagine if I talk about this, figures. Let me go over here. Yes, over here. Where is the object distance? This object, this is a incident light falling on the object. We always measure the distance from the pole sides. Okay, when I come back to this ray diagram, what is it? This is the object distance. This is the incident ray, and this is the object distance. This is the incident ray. This is the object distance. So object distance is against the incident ray. This is an incident ray. This is the direction of the object distance. So object distance is always taken with reference to from pole. So P here B, you can say P, so the object distance, AB is an object, so PB is an object distance. It is taken as negative. Same case, the image is also formed on this side only, against the incident direction. And therefore the image distance is always taken as negative. So here the object distance is negative, the image distance is also negative. Object distance is negative, this is incident ray, the object distance over here is negative, the image distance is also negative. Here also the object distance is negative. This is an incident ray and the object distance is negative. And the image is also formed on this side on this, it is negative. Here what is happening? The object distance is also negative and the image distance is also negative. Here the object distance is PB, it is negative. But the image distance is PB dash, it is with the direction of incident ray. The incident ray is moving on this side from left to right. And therefore here the image distance will be positive. So that is what it is written over here. Concave mirror, object distance is always going to be negative. But if the real image is formed, it is negative. Virtual means behind, it is positive. And likewise, the focus is always on the side of the object distance. The radius of curvature is also on the side of the object distance. And therefore they both are considered to be negative. The height of the object is positive. When is the height considered to be positive? When the image object is above the principal axis. Object is above the principal axis. I'll come to this figure later on. And when the image is formed below the principal axis, it is considered as negative. So in convex mirror, the U will be negative, but V will be positive. The virtual image is formed, therefore it is formed behind the mirror. And both the focus and radius is also positive, and the height of the object. Remember this figure very well by heart. This figure, if any numericals are asked, you are always going to be positive. Remember in this exam, they have said that they are not going to ask numericals, but they can ask, they can put a question, make a question and tell you to answer on the basis of this. So please learn at least the sign convention. They have not said that they're not going to ask you about sign conventions. So this is a spherical mirror. This is the direction of the light, that is the incident ray. We always measure the things from the pole, from this direction towards this direction, and therefore the signs against this direction of light is taken as negative. So what this direction is negative, but if behind any object is formed, image is formed, then what will happen? The symbol has to be taken positive. Object is above the principal axis. This, if it is taken, height is taken positive. If the image formed is below, then the sign is taken as negative. Below the principal axis, inverted, if it is taken as negative. But if it is virtual, it will be above the principal axis. So it is at that time the height is taken as positive. So sign conventions, the theoretical part I have written very well over here. The object is always placed on the left of the mirror, and the light from the object always fall from the left to the right. So this is an object, it is placed on the left side, and from the object, the light will be incident on the mirror in case of the concave mirror. All the distances parallel to the principal axis are measured from the pole. So distance is always measured from the pole to work on the principal axis. All the distance measured to the right of the pole is taken positive because it is going with the direction of the incident light. This is an incident light, straight it will go. So all the distances measured from the right side of the pole are taken as positive, and on the left side of the pole are taken as negative. Height perpendicular above the principal axis is taken positive, height below the principal axis is taken as negative. This is also one of the most important question it is asked. So you draw the figure and write the rules, all the convention rules over here. Remember the mirror formula. You are not going to derive over here in 10th standard. You will be learning in higher classes. So just remember the formula. 1 upon F is equal to 1 upon V plus 1 upon U. They can ask you the mirror formula. So they will tell you in exams, explain the mirror formula. So in the mirror formula, 1 upon F is equal to 1 upon V plus 1 upon U, where F is considered as a focal length, V is considered as an image distance, and U is considered as an object distance. You will have to write this. So these formulas you will have to remember about the mirror formula. The mirror formula is 1 upon F is equal to 1 upon V plus 1 upon U. The magnification is equal to height of image upon height of object. You can also say it as H is equal to H dash upon H, which is equal to minus V upon U. Let us learn about refraction of light. Till now, we learned about the reflection of light, and we learned about the mirrors, the curved mirror, the plane mirrors. Now we will be learning about refraction of light. So refraction of light means when a ray of light is going from one medium to another medium. In reflection, the light was coming back in the same medium, but here the light is going from one medium to another medium. So one transparent medium to another transparent medium. The light will bend. This is because the speed of light will become slower if it is going from a rarer medium to a denser medium. See, this is air is a rarer medium. This is a denser medium. You can see the pencil appears to bend when you put it in a water. Put it straight, it will look like this. Okay, pencil placed in exact center of the container. Pencil placed to the left of the center, and pencil placed on the far left of the container. You can just see how the pencil will look. This is because the speed of the light changes and the image will appear like this. So what is refraction of light? Refraction of light means when a ray of light goes from one medium to another medium, it will bend. Why it is bending? Because the speed of the light is changing. So let us learn about this ray of light that is falling at a point. This is a point of incidence. So at a point of incidence, this is a surface of another medium, change in medium. This is substance number 1. This is substance number 2. Let me take this as air and this is a water. And this is a point of incidence because at this point of incidence, the incident ray is falling. This is normal because the surface is straight. So I've drawn a line straight over here. So the angle between the normal and the incident ray is called as angle of incidence. Now when the ray of light is going to another medium, what will happen? It is bending, and it bends down. Then if I draw this normal extended normal line, and if I make the angle, then the angle between the refracted ray and the normal is called as angle of refraction. So this is an incident ray. This is a point of incidence. Light is moving in another medium. Now we call it as refracted ray. Okay, when it is changing a medium, the ray is called as a refracted ray. Just see this. This is a fast medium. And this is a slow medium. So what will happen? The light will bend. But always the light has to maintain its parallel movement over here. So here it is changing the medium, it is moving. So the bottom part of the incoming rays reaches slow medium first and is slowed down first, rotating the ray towards the normal line. Okay, so here it is moving first, then it will rotate towards the normal. The waves slow down and becomes bunched up as they enter the glass. So this is an air and this is a glass. So they are slowing down. Remember the contact area. It is remaining there, contact. They are not moving away the contact. It is expanding, and slowly they speed up and spread out. It's the leaf. Okay, they are spreading out as the leaf. Here the distances you can see. Here you can see the change in distance, and here again they are spreading out. So refraction is a bending or change in direction of the light when it travels from one medium to another medium. For example, air to the water. It is used in building lenses. Your different type of glasses that you're wearing are made up of lenses. The bending of light is due to different media, slowing light down by different amount. The more light slows down, the more it is refracted. This is an experiment of a glass slab. This is a glass slab. Let us take a ray of light falling at a point of incidence B. This is a ray AB. It is an incident ray. At the point B, the ray of light will bend. It is a BC. At point C, again the ray of light is moving. So when you keep a glass slab over here, draw a line, see from the other side, draw a line CD. This AB is called as incident ray. The CD is called as a emergent ray. In between the BC ray, join these two rays, it is called as a refracted ray. This is a normal line to the surface. Again, this is normal to the surface. So the angle between the normal and the incident ray is called as angle of incidence. The angle between this is a refracted ray, and the normal is called as refraction. We have named here incidence 1 and refracted 1. Now over here again, this refracted ray with the normal makes a refraction angle 2, and again when it's moving out, it will give the angle that is incidence number 2. Over here, if you remember that the angle I is greater and angle R is smaller. That is when a ray of light is moving from an rarer medium to a denser medium, it will bend towards the normal. And here over here, you can see the angle R is less and it is moving out. That is, the denser medium is that of a glass and a rarer medium is of the air. When it is moving out, what is happening? The angle is again increasing. So when a ray of light moves from a denser medium to a rarer medium, the angle is increasing. That it is bending away from the normal. This experiment shows us the rules of the ray of refraction, that when the ray of light moves from a rarer medium to a denser medium, the refracted ray will move towards the normal. And when the ray of light moves from a denser medium to a rarer medium, the ray of light will move away from the. However, done this experiment, take a glass slab, draw a line on one side, draw the outline of the glass slab, draw a line on one side, see from the other side, make a line, straight line by seeing that. When you make a line straight, you will see that the line is over here. Join these two lines. So this is an incident ray, this is a refracted ray, and this is an emergent ray. Now, draw this incident ray of light straight. What will happen if the light will pass straight? So this I have drawn. This light will go straight, but that is not happening in the case. The light will bend. So that means from C, if I make a perpendicular line, what is a shift? This distance, perpendicular distance between the incident ray and the emergent ray is called as lateral displacement. It is also called as lateral shift. So what is a lateral shift? It is a perpendicular distance between the incident ray, this is an extended incident ray, and this is an emergent ray. So what is the lateral displacement? It is a perpendicular distance between the original path traced by the incident ray and the path traced by the emergent ray coming out from the glass. Following are the factors on which the lateral displacement depends. It depends upon the thickness of the glass. It depends upon the refractive index of the glass slab, and it also depends upon the angle at which the incident ray enters the glass slab. So law number 1, the incident ray, the refracted ray, and the normal to the uh, interference of the two transparent media, that is the point of the incidence, they all are going to lie in the same plane. The second law is called as the Snell's law. Snell's law says the ratio of sine of angle of incidence to the sine of refraction is constant. The answer is going to remain the same. This is a Snell law. Light bends as it goes from one medium to another because it is going to change the speed. Compare the bend to the normal, just like a reflection. Light bends towards the normal when it enters a denser medium and slows down. Light bends away from the normal when it enters a less denser medium and it speeds up. So this ray of incident ray, it is moving to a glass, from air to glass. So the speed will become slow. And from here, the glass to outside, when the ray is going, the speed will again go up. And in case of normal, the ray of light is always going to go straight. Okay. The Snell's law, and sine of angle of incidence is always equal to sine of angle of refraction. What is refractive index? The refractive index of a substance is the measure of the speed of light in that substance. It is expressed as the ratio of speed of light in vacuum to that in the considered medium. So reflective index eta, n eta it is equal to velocity of light in vacuum upon velocity of light in the particular medium. Remember, the refractive index of water is 1.33. That means light travels 1.33 times as fast in vacuum than in water. Okay, so in vacuum, the speed of light is 1.33 times more than that in water. So when light is moving from the air to water, we call it as endpoint, eta is 1.3. Refractive index is 1.3. Refracting index is 1.5 over here. That means light is traveling 1.5 times less than that vacuum. Or as I can say the speed of light in vacuum is 1.8 times more than that in diamond. Diamond refractive index is not 1.8, depends on different varieties of diamond. The diamond which has got a very good view and a pure diamond, the refractive index is 2.542, we say 2.42, and it is the highest. You can always see the diamonds shining over there. What is relative refractive index? Relative refractive index is between the two medium, like air and water. If I want to find out the refractive index of air only, then I'll have to take the velocity of light of vacuum to velocity of light in air. If I want to find out the refractive index of water, then I'll have to obtain the velocity of light of in vacuum to that of water. It is called, but okay, it is called as absolute refractive index. That is how we get the figure that refractive index of water is 1.33. But if I want to find the relative refractive index, that between the air and water, so it will be refractive index of in air to refractive index of water. Okay, so it will be between the two different mediums over here. So refractive index of medium 2 with respect to medium 1. Over here, if I take this as medium 1 and this as medium 2, this is a normal ray of light is falling over here at the point of incidence and it is coming near the normal. This is theta 1 angle, this is theta 2 angle. So refractive index, that is the ray of light, is going from medium 1 to medium 2. Okay, so refractive index of medium 2 I want to find out with respect to medium 1. means speed of light in medium 1 upon speed of light in medium 2. Okay, I want to find the refractive index, how much light is bending in the medium 2. So that I have to calculate with respect to the medium 1. That means if I have to know how much the speed of light is in, velocity of light is there in medium 1 upon speed of light in medium 2. It is also called as eta 21, which is equal to speed of light in medium 1 upon speed of light in medium 2. Opposite is also true. If I want to take the ray of light going from medium 2 to medium 1, okay, that means I want to find out the refractive index of the medium 1 with respect to medium 2. So I'll have to calculate the speed of light in medium 2 to speed of light in the medium 1. And I can say eta 12 is equal to speed of light in medium 2 upon speed of light in medium 1. So what is absolute refractive index? Absolute refractive index means ratio of the speed of light in vacuum to the speed of light in that particular material. It is denoted eta is equal to C upon V. C means the speed of light in air, or I can rather put it in bracket and say vacuum upon speed of light in that particular material. Diamond, I told you it is 2.42. Okay, that it must have been written quartz over there. Different. It is SiO2, silica. It is. So now speed of light over here, it is coming inside the diamond. So what is it? It is bending very near to the normal. That means what is happening? The value is 2.42. Speed of light in glass, the angle is 34.5 more. The value over is 1.5. Speed of light is in water, it is 1.6, 40.6. It is increasing. The value is 1.33. So 40.6, what is happening? 40.6, 1.33 is the refractive index. 1.5 is the refractive index and 2.42 is the refractive. Saying is that it is coming nearer to it, the refractive index value is increasing. Absolute refractive index of different materials. I'll just tell you to which you have to remember. Air 1.0003. Then you have to remember alcohol and kerosene 1.3 and kerosene 1.44. Then the glass, it is 1.52. Then remember ruby, it was asked in one question paper last year only. Ruby 1.71. Sorry. And sapphire 1.55. Diamond is 2.42. Highest is diamond. So remember diamond, air, water, kerosene, and ruby. Okay. Quartz, I told you, it will be nearly 1.46. So refractive index, I think you all know very well what is a refractive index. We will know the speed of light in different mediums on the basis of refractive index. There is one question that it is asked, and it is there in the textual part also. If I put kerosene in water, what will happen? The kerosene will float in water. So whose refractive index is more, kerosene or water? I think we know the refractive index of water is 1.0003, and the refractive index of kerosene, I told you to remember, it is 1.44. But yet kerosene is floating on water. So this is refractive index. The refractive index has got nothing to do with the density. So they've confused the question to you. Don't confuse yourself with the refractive index and the density. Because the density of kerosene is less, it is going to float on water. But refractive index means totally a different topic. It is a which medium? It is denser medium than the air medium. Okay, so don't confuse yourself with the refractive index and density topics. Snell's formula, eta 1 sine theta 1 is equal to eta 2 sine theta 2 over here when there are two mediums taken. Now we will learn about the topic that is called as total internal reflection. It is a phenomenon that is taking place because of the reflection and refraction. Now let us take, it always takes place when a ray of light goes from a denser medium to a rarer medium. So rule number 1, remember whenever we are talking about the total internal reflection, we have to listen that the ray of light goes from a denser medium towards a rarer medium. So water is a denser medium, air is a rarer medium. So when a ray of light goes from a denser medium to a rarer medium, what will happen? It will bend away from the normal. So this angle will be less, theta 1, and theta 2 angle will be more. Now, if further and further, if we say the angle is, what is happening? Increasing. We are increasing the angle will increase. We are increasing the angle will increase. And after some time, what is going to happen? The ray of light, when it is refracting, it is making a more angle. A time will come when it will pass only through the surface. What is a critical angle? A critical angle is an angle whose refracted angle is 90 degrees. So this is a critical angle. Theta 1 is a critical angle. It is between the normal and the incident ray. Okay. So when the refracted, after the refracted angle is 90 degree, the ray, instead of going in the other medium, will come back in the same medium. See, this is another medium. This is at the border, reflected ray. Any other reflected rays come back in the same medium. That is, reflection has taken place. This was a refraction. This was also refraction, and this is reflection. FLEC. It has come back in the same medium, and this means total internal reflection has taken place. So total internal reflection takes place when the after the critical angle. Okay, so when a critical angle is formed, after that, the total ray, instead of going in another medium, will come back in the same medium. What is the difference between the mirror and the lens? Mirror, the rays are coming back in the same medium. Lens, the rays are passing out. It is going in another medium. In this medium, it has passed and it has gone out. See. So now we will be learning about lenses. We will be learning about concave lens and convex lenses. So before going there, let us understand the difference between a mirror and the lens. Mirror means there is a glassy surface and backside is an opaque. Lens means it is totally transparent. The example is that of glass, plastics. Mirrors can be plain or it can be curved. Lenses can be curved. It can be curved only on one side also, and it can be curved on both sides also. Mirrors, the principle is law of reflection. Lenses, the mirrors are the principles are laws of refraction. In mirror formula, you have to write 1 upon f is equal to 1 upon v plus 1 upon u. And in lens formula, you will have to remember 1 upon v minus 1 upon u. This is plus and this is minus. Okay, remember this plus sign and this minus sign. V means object distance, u means image distance, f means the focal length. So how many types of lenses are there? Over here, this is a biconvex lens, means both the sides are curved outside. It is a converging lens, opposite to that of the mirror. In mirror, the convex mirror was a diverging mirror. The concave mirror was a converging mirror, but concave lens is a diverging lens. Okay, they're opposite to each other. So they're biconvex, means both the sides are curved inside. and by concave and by convex, both the sides are curved outside. Plano-convex means only one side is curved. A plano-concave means one side is curved inside. Okay, fine. How to form a convex mirror? Convex lens. Now I have to talk about lenses. How to form a convex lens? Take two pyramids and with the bases keep on each other. A convex lens is formed. And instead of bases, I'll keep the tips on the side. The bases are on the opposite sides. Bring the tip. A convex lens is formed. Okay. Convex lenses are called as converging lens because when the ray of light, parallel ray of light, they converge and they meet at the focus. They have to go on the other side because light is going to pass. And when the parallel ray of light passes through the concave lens, they diverge. They are called as diverging lens. This is a focus, the point at which all the parallel rays to the principal axis meet. And these are diverging, but if I extend it on the back side, they meet. It is called as a focus. How a convex lens is formed? Take two spheres, and in between, this is an overlapping part. A convex lens is formed. This is a center. It is called as an optical center. If I make this lens circle, again, I'll go to that slide to explain you. So this, I can make a circle from here on this side. And here I can make a circle on this side. Okay, so this one circle and there one circle. Here also I can make a circle, sphere, full one circle on this side and one circle. So what will be the center of this circle called as center of curvature, and this side another center of curvature. Here also there are two center of curvatures, and in between is an optical center. So imagine this is a convex lens. If I make a circle over here, this is C2, and if I make over here, this is C1. Why? This is an incident ray. We are going to allow the ray to fall from here. Therefore, this is C1 and we are kept at C2. Even you can write C1 over here and C2 over here. Okay, but then you have to be very specific that which side the ray is coming from, which side the ray is coming. This is a principal axis. The line joining the optical center and center of curvature is called as principal axis. In between optical center and center of curvature will be the which part? Focus. That point is called focus, and the distance between the focus and the optical center is called as a focal length. The distance between the optical center and the center of curvature is called as radius of curvature. See, this distance is called as radius of curvature. This is a concave lens, as I told you. Okay, this is a radius of curvature. This will be the optical center in between. A focal length can be positive and it can be negative. A positive focal length means that the focal point of the lens is on the other side of the lens from where the object is placed. Focal length is on the other side. On the other hand, a negative focal length means that the focal point is on the same side of the lens where the object is placed. The rules are going to remain the same like we did it in the mirror. When the ray of light is parallel to the principal axis, it will go on the other side and pass through the focus. Okay, rule number 2, when the ray of light is passing through the focus, it will be parallel to the principal axis. And when the ray of light is passing to the center, it will go straight. So rules for the convex lens is rule number 1. When the ray is parallel to the principal axis, it will pass through the focus. When the ray is passing through the focus, it will be parallel to the principal axis. And when the ray is passing through the optical center, it will always go straight. On the basis of this, we are going to draw different ray diagrams. Here we are going to draw the ray diagrams of the convex lenses. Again, I will go with the exception case one, the last case within the focus. Within the focus, the image formed is virtual. Dotted line shows that it is which one? The virtual image. And in case of convex lens, the image obtained is virtual and large. Rule number one, when a ray is parallel to the principal axis, it will pass through the focus. And when the ray is passing through the optical center, it is going straight. So these two are never going to meet. They're going apart. So I'll extend it on the back side and they appear to meet, and the image obtained is larger one. The images appear to meet, that is why it is virtual. They are not actually meeting. It is always erect and it is larger in size. Rest at different positions we will see. At infinity, say the sun again. So when the parallel ray of light are passing through the sun and is passing through a convex lens, they all will focus and point. Take a convex lens and let the sun image pass through it, and you can keep a paper over here at the focus part. It will burn. Imagine that is a strong light. That you can do this experiment at home. If you have a convex lens, focus it with the help of sun, and the rays are coming to the sun, and try to keep the paper exactly at the focus. You will automatically come, because this place will get so much heated up that the ray will burn. Second, where is the object placed? Beyond C. Rule number one, the ray of light is parallel to the principal axis. It will pass through the focus. And if it passes through the object center, optical center, then it will go straight. The rays are meeting after refraction, and that is why an inverted and smaller image is formed. Case number 3, it is kept at C. C is also called as 2F. When the ray of object is placed over here, apply rule number 1. Ray of light is parallel to the principal axis. It will pass through the focus. Another is passing through the optical center, and image is formed inverted at C, center of curvature on the other side. The image is real, it is inverted, and it is of the same size of the object. Now bring the object closer, that is between F and C. Rule number 1, the ray of light is passing through the parallel to the principal axis. It will pass through the focus. The ray of light is passing through the optical center. They are meeting beyond C. The image that is formed over here is larger. Since the rays are meeting, it is real. Now keep the ray object at focus, that is F. What will happen? When the apply rule number 1, ray of light is parallel to the principal axis, will pass through the focus. Ray of light is passing through the optical center. What will happen? If let it move ahead, at distance, they will meet. So at focus, as the image formed is at infinity. At infinity, image is formed at focus. So this is the chart that you have to remember. The position of object at different places: at infinity, beyond 2F, at 2F, between F and 2F, at focus, between the optical center and the focus, and we always also call it as within the focus. And that is how the image is formed. Last, within the focus, image is virtually erect. Rest cases, always the image formed is real and inverted. The image that is formed, object is at infinity, image is at focus, it is beyond 2F, the image is between F and 2F, at F, between F and 2F, beyond 2F, at F, at infinity. And you can see how the highly diminished image, the point-like image, is slowly and slowly becoming bigger and bigger, and it is highly enlarged. There are sign conventions for the spherical lenses also. This is the direction of incident ray. The direction is always taken as positive. So if the distance is measured from the optical center towards the object distance is always negative. And if the image is formed towards this side in the direction of incident ray, then the distance is always taken as positive. If the height above the principal axis is considered to be positive, and the image that is formed below the principal axis, then the height is always taken negative. Okay. Let it be a convex lens or a concave lens. So again, I have repeated the sign convention for the spherical lens. Just go through this again. Now, cases for the concave lenses, rules, there are 3 rules. It is a diverging lens. So when the ray of light is parallel to the principal axis, it is diverging, it appears to meet to the focus. When the ray of light is passing through the focus, here it is appearing to meet to the focus, it will be parallel to the principal axis on the other side. And when the ray of light is passing through the center, it will go straight. How is the image formed over here? There's only one type of image that is formed, and the image is virtual, and it is always small. So this is the parallel rays for coming to it. It is diverging. The diverging rays are meeting at the focus. Okay, so when the object is at infinity. So when the object is beyond at any places between the infinity and the center, let it be over here. One of the rays going straight parallel to the principal axis. It is diverging. Let it come back and appear to pass through the focus. Another ray of light is passing through the center, optical center. Here they are meeting. The image formed is erect and it is always small. Even if I bring the object more nearer on F also, then also the image will be virtual, erect and small. Please remember it. Image formed by the concave lens. See, beyond 2F, virtual and small. Between F and 2F, virtual and small. Beyond F, virtual and small. So they can also confuse you, like I told you in case of convex mirror. Same case is about concave lens. Convex mirror, remember? Huh? Same case is that with the concave. Anywhere you keep it. So if they ask you about if it is kept at 2F of a concave lens, don't get confused. Imagine that in a concave lens, the image is only of one type. It is virtual, erect, and small. The lens formula and the magnification, as I told you, the lens formula is 1 upon V minus 1 upon U is equal to 1 upon F. V means the image distance, U means the object distance. Magnification is the ratio of height of the image upon height of object. If they ask you just the definition of magnification, right, it is the ratio of image height upon object height. If they asked you about the lens, right ahead image of lens upon height of object of the lens in case of lens. And even mirror, you need not worry, it is going to be image height upon object height, and M is equal to V upon U. मिरर फॉर्मूला कैसा था? मिरर फॉर्मूला में मैग्निफिकेशन M कैसा था? माइनस V upon U. And magnification in case of lens is positive V upon U. Let us understand the last topic of this chapter, that is the power of a lens. Power is inverse of focal length, or focal length is the inverse of power. The unit of focal length is meter, and therefore the unit of power becomes meter inverse 1. It is also called as diopter. You can also give a symbol capital D. 1 diopter is equal to 1 meter. The power of a convex lens is always positive, and the power of concave lens is always negative. The short-sighted people always wear a lens that is a concave lens, and their power, if you go find that the doctor, the ophthalmologist, what they have prescribed and written on the card when they went to check their eyes. If they are short-sighted, the diopter reading, the power reading will be always in minus. And in case of long-sighted people, that the people with age, when they get the spectacles, they always wear a lens that is positive, and that is, the lens is always convex lens. So define power of the lens. What is the SI unit of power? Power is the reciprocal of focal length of the lens. P is equal to 1 upon F, and the SI unit is 1 diopter is equal to 1 upon meter, and the unit of power is diopter, or you can say meter inverse 1. This is a small example where you should understand the sign convention. Far point of an eye, of a defective eye, that is the V, is equal to minus 80. Object distance. The object distance U is at infinity. Now find the nature and power of the corrective lens. So what is the lens formula? The lens formula is 1 upon V is minus 1 upon U is equal to 1 upon F. So 1 upon F focal length is equal to 1 upon minus 80 in minus 1 upon minus 8 infinity. So 1 upon F is equal to 1 upon infinity means 0. So minus minus will become plus. So it is plus 0. 1 upon F is equal to minus 1 upon 80. Inverse it, F is equal to minus 80. Therefore, the corrective lens should have a focal length of 80 centimeter. Now we are interested in finding out the power of the lens. So power is the inverse of the focal length. The P is equal to 1 upon F. Okay, now as focal length is in centimeters, I have to convert this 1 meter into is equal to 100 centimeters. So I'll be converting the upper part, that is 1 is equal to 100 upon minus 80. Or else here I can say that 80 upon 100. So 100 goes up that way. Therefore, P is equal to minus 1.25 D diopter. And therefore, the corrective lens is minus. Minus indicates which type of a lens? It is a concave lens. And concave lens is which type of a lens? It is a diverging lens. And what is the power? Minus 1.25. So you should be knowing all this very well. Centimeter has to be converted into meter because meter and diopters are connected. So 80 centimeter, in order to convert it into meter, I'll have to write 80 upon 100. 100 will go up, and that is how I got 1.25. An object is placed at the distance of 60 centimeter from the concave lens of a focal length 30 centimeter. So it is a concave lens, and the object is placed at 60 centimeter from the concave lens. So the object distance is always taken minus 60. The focal length is 30 centimeter. The focal length of a concave lens is always negative because the image is always formed on the same side. Therefore, the focal length is also taken as minus 30 centimeter. At least you should know how to make a sign convention. Thank you so much.